Good morning students. In this lecture we are going to discuss about the domain theory of ferromagnetism. Ways proposed to the concept of domains in order to explain the ferromagnetic material. Ferromagnetic material possesses the spontaneous magnetization. First let us see what is domain. So domains present in a ferromagnetic material is responsible for the spontaneous magnetization present in the ferromagnetic material. First let us see what is domain. The group of atomic dipoles organized in small bounded region within the ferromagnetic material is known as the magnetic domains. So a group of atomic dipoles organized in small boundary. Organized means aligned parallel in a with a small boundary within the ferromagnetic material. So a ferromagnetic material consists of several number of domains. In each domain, the atomic dipoles are aligned in parallel manner. Uh, because of which the ferromagnetic material possesses the spontaneous magnetization. Every material is tries to attain a stable form by minimizing its energy. The domain structure of the material is a one that minimizes the Gibbs free energy of the material, and this is given by the free energy equation proposed by Landau and Lifshitz in the year 1935. This free energy Eg is given by this expression. The free energy Eg is the sum of exchange energy magnetostatic energy EMS, anisotropy energy, magnetostrictive energy, and Zeeman energy. The Zeeman energy, the last term Ez, is known as the Zeeman energy that comes to play the role in the presence of external field. Hence, we will not discuss it in this lecture. Now let us discuss one by one. First, exchange energy. Some ferromagnetic materials like iron, cobalt and nickel have very high value of magnetic moment, that is due to the presence of unpaired electrons. This arises due to the strong quantum mechanical exchange interactions between the dipoles, and this is called exchange energy. So the exchange energy, if that is minimum, the spins are aligned in parallel manner. So this will be less for parallel spin alignment when compared to the anti-parallel spin alignment. If the spins are aligned in parallel manner, the exchange energy is minimum. If it is aligned in anti-parallel manner, the exchange energy is higher. Hence, all the dipoles will first align in the same direction, creating north and south pole due to its self-magnetic moment. So, due to the self-magnetic moment, due to the exchange interaction, and the spins, atomic dipoles align themselves in the parallel to each other. So, as a result, it shows the magnetic moment due to parallel spins. Next, magnetostatic energy. Due to the parallel alignment of spin magnetic moment, the magnetic lines of force will be created outside the material. So, due to the parallel alignment of spin magnetic moment, the magnetic lines of forces will be created outside the material. So, look at this. So, due to the parallel alignment of spin, it has become a magnet. So due to the parallel alignment of spin, the magnetic lines of force will be created outside this material. The created magnetic lines of forces will pass through the material also, that will coming outside the domain. So this self energy created by the magnetization in some part of the sample and the other part uh, is called the magnetostatic energy, and it depends on the volume occupied by the magnetic field, which means this field. So already the aligned spin that produces this field, this passing magnetic field, that will create a magnetization in some parts of the sample. So on the other part, then it is called the magnetostatic energy. So this depends on the volume occupied by the magnetic field extending outside the domain and the sample. Anisotropy energy. By dividing a single domain into n number of domains in a ferromagnetic material, the magnetostatic energy can be reduced into the amount of 1 by nth of the magnetic energy of a single domain. So a single domain that is subdivided into n number of domains, the magnetostatic energy can be reduced 1 by nth of the magnetic energy of the single domains. This is done by spins changing their direction, thereby creating a Bloch wall. So if the spin is changing their direction, so in between a Bloch wall is created. So Bloch wall is the separation wall of two different domains. So the energy is required to shift the spin from one direction to another direction. So usually the atom lies in the soft direction. So naturally the spins in the atom that that oriented in the soft direction, by creating a Bloch wall, that means we are subdividing the domains. The spins has to align in the align from soft direction to hard direction. So as the energy is required to shift the spin from soft direction to hard direction, some work has to be done, that may be by that is done by the external applied magnetic field to turn them into the hard direction. So this difference between the energy to produce the saturation in easy and hard direction is called the crystal anisotropy energy. So look at this picture. This consists of two domains. So this domain is further subdivided into two part. So this is separated by a Bloch wall. So the spin is in the whole volume. The spin is lies in this direction. But if it is divided, the spins are aligned in opposite direction. So to align this spin into this direction, the external applied field or external work has to done over the dipole. So the difference between the energy to produce the saturation in easy and hard direction, that is called as the crystal anisotropy energy. So look at this picture. So this is the crystal structure of body centered cubic crystal structure of iron atom. So this is the different direction in this BCC structure. So this direction 100 direction is known as the EC direction, and this direction 110 is the medium, and this direction is known as the hard direction 111. So look at this picture. The magnetization. So for this direction 100 direction, the magnetization. So quickly the magnetization, if a small field is applied, the saturation magnetization is occur. So this direction in the EC direction, a small energy will produce as small applied magnetic field will produce as the saturation magnetization. But in these two direction, the applied magnetic energy, the applied magnetic field increases, then the magnetization is also increases, then it reaches the saturation magnetization. Especially for this 111 plane, the large amount of applied magnetic field is required to produce the saturation magnetization. Next, Bloch Wall Energy. The process of changing their direction of spin from one to another can be either gradual or abrupt, and this creates a Bloch wall. So Bloch wall it generally lies between the two regions which is having spin in the different orientations. The process of changing the direction of spins from one to another can be either gradual or abrupt. That means it will occur slowly or it will occur quickly. If the change is happened slowly, the exchange energy is lower, but the anisotropy energy is larger. If the change in spin occurs slowly, the exchange energy is lower in this case, but the anisotropy energy is larger. If the change is abrupt, the exchange energy is larger, but anisotropy energy is lesser. So it is maintaining the balance between these two. The Bloch wall is a compromise between these two. The wider the wall, crystalline isotropy energy is increases since large number of dipole forced to line in the hard direction from the AC direction. Hence, the width of the wall will reach an equilibrium value. Bloch wall energy is the sum of exchange energy plus anisotropy energy. From this equation, it is known that the domain wall formation requires extra energy that is known as domain wall energy, which is proportional to the area of the domain wall, that is square of the domain size. The field energy is proportional to the volume of the domain, that is cube of the domain size. As domain becomes smaller, the net energy saved by splitting decreases because the net energy reduces is the difference between the magnetic field energy saved and the additional energy required to create the domain wall. The domains will go on splitting into smaller and smaller region until the energy required to create an additional domain wall just equal to the field energy saved. So the splitting will goes on until the energy required to create an additional domain wall just equal to the field energy saved. So only such domain size will be stable. This is of the order of 10 power minus 4 to 10 power minus 6 meter in most of the materials. So look at this picture. This is the domain wall. So this side the alignment will be in this direction, but beyond the domain wall the alignment will be in the opposite sense. So look at this picture. This is the relation between the wall width and the energy. So this is the exchange energy. If the wall width increases, the exchange energy decreases. If the wall width increases, the anisotropy energy is also increases. So the Bloch wall energy is sum of these two. So the Bloch wall energy is first decreases with the increase of the wall width. It reaches a minimum. So in this region the exchange energy is dominated. So beyond this, so in this region these two is balanced. So beyond this region the wall width increases, the Bloch wall energy is also increases. So in this region the anisotropy energy is more than the exchange energy. Next, magnetostrictive energy. Finally, the flux closure domains will form with magnetization at right angles to other domain. This will reduce the magnetostatic energy to nearly zero, but it will increases the anisotropy energy. So and also it will cause small mechanical stresses in the material. So this phenomenon is termed as the magneto-elastic anisotropy or simply magnetostrictive energy. Hence, the closure domains formation require additional energy and which will be formed only when the magnetostatic energy saved is more than the sum of exchange energy, crystalline anisotropy energy and magnetostrictive energy. So the magnetostrictive energy saved is greater than exchange energy, anisotropy energy and magnetostatic energy saved is greater than exchange energy, anisotropy energy and magnetostrictive energy. So finally the size of the domain will be stable when the free energy will be minimum, which means Eg is equal to sum of exchange energy, sum of magnetostatic energy, anisotropy energy and magnetostrictive energy. So these three is increases proportionally, that will reduces the magnetostatic energy. Okay students, thank you.